Now, I am going to do one very simple example. This is also my favorite example. This example is very simple, but it will illustrate all the aspects that we have learned till now about the Lagrangian formulation. So, here let me start by considering a rigid hoop. Okay. Now, this hoop is uniform, that means its mass is distributed uniformly over the hoop, and let us say its radius is r. Okay. Now, this is a rigid body. So, of course, rigid body normally we consider it as collection of many particles, and then there are also large number of holonomic constraints that the distance between each particle is constant. Okay, each pair of particles is constant. So, I am going to assume that we have used all those holonomic constraints, and then the system reduces to, the number of degrees of the system reduces to just 3. Remember, this hoop is allowed to move only in xy plane and it can rotate. So, the most common set of generalized coordinates that I would use is the x, y and theta, where x and y would be the coordinates of the center of the hoop. So, this would be your x and y coordinate. Now, on the hoop I have marked one piece or put one red mark on the rim there, and this is our marker. Okay. So, look at this position vector pointing to that red marker, and this vector makes an angle of theta with the horizontal. So, these are the 3 generalized coordinates that I am going to use. Now, for the calculation purpose, I am also going to again think of this hoop as made up of several small segments. Okay. So, there are a large number of small segments, and of course, we will sort of think of this as a continuous system if the number of segments become very large or tends to infinity. And then we will number these as 0, first segment, and so on, and somewhere here you have ith segment, and total number of segments there is n. So, the n minus 1, the indexing goes from 0 to n minus 1. Now, the position vector and mass of each one of those segments would be m by n. I will also denote it by delta m later in the lecture. Now, consider this particle I or segment I, and then you have this position vector to this. Let me call this position vector Ri. This position vector now I must express in terms of our generalized coordinates. So, for each segment you have this transformation from Cartesian coordinates to the generalized coordinates. Okay. So, here the position of ith vector Ri would be given by, so let us mark this angle as alpha I. Okay. Since there are n segments, this alpha I clearly is 2 pi by n times I. Okay. And the total angle from the horizontal now is theta plus alpha I. So, the x coordinate or x component of your position vector of ith particle is given by x plus r times theta plus alpha I, and then y coordinate would become y is equal to r times sine of theta plus alpha I, and alpha I is of course this. Now, what would be the configuration space of this system? You remember there probably are large number of particles and there is a big configuration space, but what is the accessible configuration space? Remember, number of degrees of freedom is 3, so it is 3 dimensional, and I have 3 generalized coordinates. I am going to plot this configuration space as shown in this figure, where I plot x axis here, y coordinate on this axis and the theta coordinate here on this axis. Okay. Also remember that theta is equal to 0 plane, which is actually xy plane, and theta is equal to 2 pi plane. These two planes are same. That means theta actually indicates the rotation of the disk, of the hoop. So, when hoop goes through a rotation of 2 pi, well, you have the same configuration of the system, which means this plane here, theta is equal to 2 pi, is somehow joined to theta is equal to 0 plane. Now, how do I show this in this configuration space? So, clearly in some higher dimensional space, this would be something like a hypercylinder. Now, when we show it in this 3 dimensional, because its visualization in 3 dimension has to be something like this. So, in this case we will show the trajectories. The trajectories, remember, are restricted to the slab between theta is equal to 0 and theta is equal to 2 pi. All these trajectories, as soon as they pass through 2 pi, they re-enter from theta is equal to 0. Okay, that is how it will happen. But then we can also show the trajectories continuously going out of this, and what we have to realize is that the points which are here are actually same as points which are here, where x and y coordinate remain same. You have to just subtract 2 pi from the theta coordinate. So, that will actually give the configuration of the system. Okay. What kind of motion this hoop can have? There are several possibilities there. Now, the simplest one of them is this. If I keep theta coordinate fixed and y coordinate fixed, just move x coordinate, that means the hoop actually travels along x axis, keeping its y coordinate constant, and theta is also constant. So, it is not rotating. So, as you can see in the figure, the hoop is just simply translating along x axis. The other possibility, of course, is when you keep x constant, theta constant, and vary y, and as you see in this animation, the hoop is simply traveling in the direction of y. Okay. Then we can of course consider the other one, where x and y are constant and only theta is changing. What does that mean? The center of the disk is fixed, it is not moving here. What is moving? The only disk is rotating, the hoop is rotating about its center. Okay. So, this is, and then of course, you can have variety of other possibilities there. One of them could be, as you can see, it is a simple rolling of the hoop on the surface. Okay. In this case, that surface is actually a line which is x axis, and look at its trajectory in configuration space. In configuration space, of course, theta changes from 2 pi to 0 as x coordinate increases, and in this particular rolling, of course, y coordinate is fixed. And why is this theta going from 2 pi to 0? That is because, remember, we measured theta in the counterclockwise direction, and in the rolling, the hoop is rolling in the clockwise direction. That means theta is actually decreasing. Okay. And then of course, you can have large number of possibilities. How about this one? See, when I am showing you all these trajectories, I have not given you the force configuration. There is some force configuration which will make this happen. Okay. So, in this case, it does look like a motion under gravity, but it is little slow. It's more like a balloon just bouncing slowly. So, not just the gravity is acting, but there must be air resistance which slows the motion down and so on. Okay. All right. So, these are all representative trajectories there, and there are infinitely many varieties there. Now, what I am going to do is, now I am going to specify the force configuration in the problem. The first thing we will do is put the gravity in. Okay. So, let us start by putting gravity. So, your disk moves in 2-dimensional space and the gravity is in minus y direction. Okay. So, you remember x direction was this, y direction is this. Oh, sorry. The other way around, this is your x direction, this is your y direction, and then the gravitational acceleration is pointing downwards. Now, let us write down the Lagrangian. So, Lagrangian will be for each segment, the Lagrangian is half delta m is the mass of each segment. So, I am looking at ith segment here, this one, and for ith segment the mass is delta m, and then the speed of ith segment, this is x I dot square plus y I dot square and minus of course the gravitational potential, which is delta m times g times y I. And eventually of course I have written this in terms of the coordinates of individual segments. I want to write this in terms of generalized coordinates, and remember the Lagrangian is function of x, y, theta, and I have forgotten to write here x dot, y dot and theta dot. So, how do I calculate this? Start by looking at the transformations. So, I know x I is equal to x plus r times cos theta I plus alpha I, and then x I dot is just taking its derivative. So, you get x dot and derivative of cos is minus sign multiplied by r and multiplied by theta dot. And similarly, here y coordinate is y plus r sin theta plus alpha I, take its derivative with respect to time, then you get y I dot is equal to y dot plus r times theta dot and then cos of theta plus alpha I. Okay. Now, what I am supposed to do is square this and put it back into the Lagrangian. Y I is also known, put it back there. Okay. It is an easy calculation. You can immediately see when I do x I dot square, I get x dot square. So, for each segment, the first term here, this term here will contribute 1/2 delta m x dot square, and because it is a constant term summed over n segments, it is n times delta m x dot square. You can immediately see this will come to half mx dot square. Fine. This linear terms in the square, they actually add up to 0, and for that we have this identity here. You can easily prove this identity. You can look at, for example, e to the power I theta plus 2 pi. So, I will call this as j by n and summed over j. So, if you want to prove this, look at this. This is a geometric series. What is its sum? And then use the decomposition of exponential function in terms of sine and cos, and you prove this identity. Once you prove this identity, this is the term that appears in the linear term of the square. So, that will also become 0, and the last term here of course again will make use of this identity here. So, you will have sum over. So, this term if you want I can write here, there is a summation over I, then delta m g, and there is a y plus sin theta plus alpha I. Okay. So, you can immediately see you will get m, so n times delta m, which is m g y as one term, and the second term is summation over sin theta and plus sin theta plus alpha I, and that term of course by this identity becomes 0. So, your total Lagrangian now becomes m by 2 x dot square plus y dot square plus m by 2 r square theta dot square and minus mgy. Oh, of course, we could have written that without doing all this calculation, but I wanted to do this calculation for some other purpose when we are going to calculate actual forces, the other forces in the system. And the one quick look at this Lagrangian immediately tells us that x and theta, they are ignorable coordinates or cyclic coordinates. What does that mean? The linear momentum in x direction is conserved and the angular momentum about the center of the disk is also conserved. So, these are the two conserved quantities. What kind of motions are possible? You can write down now Lagrange's equations. Now, we have Lagrangian with only one force in the system, and that force is the gravity. So, let us write down the equations of motion, and they are straightforward. We of course know what the answer would be. The x component, x coordinate simply moves linearly with t, and the y of course is proportional to initial velocity into t minus half gt square. And the third one, which is theta coordinate, also moves linearly with t, changes linearly with t with some omega naught. Remember, because the angular momentum is conserved quantity, whatever spin that you give to the hoop in the initial at the initial point, this will follow a trajectory, parabolic trajectory with the same spin throughout the trajectory. So, that is you can see the motion which is shown here, the black dot as it moves, the hoop moves, and you can see that hoop is actually spinning about its axis. And there is no restriction here. Okay. So, this was a simple case, a simple Lagrangian with one gravity force, and we already knew the answers. Now, I am going to put one constraint here. Okay. Let us take a situation where you have this hoop which can move in vertical plane. There is still a gravitational acceleration pointing down, and now I am going to put this ramp. This ramp makes an angle of 30 degrees here. 30 degrees. So, this angle is 30 degrees. What happens here? The hoop cannot go below the ramp. So, and we will of course assume that the ramp extends to infinity, and which means the center of that hoop cannot go below this red line here, and that is the constraint. And then I will set up my coordinate system such that this red line passes. So, this is your y axis and this one here is your x axis, and red line passes through the origin of this coordinate system, which means I can now write down this constraint as y minus x tan 30 degrees must be always greater than or equal to 0. What kind of constraint is this? It is of course independent of time, but it is a non-holonomic and it is in the equation form, it is not in the Pfaffian form. There is very little use of this particular constraint to us in the problem solving. Now, what force, what is the constraint force for this one? That is of course the normal reaction from the ramp. And in addition, we will also assume that there is a friction, which means whenever the hoop touches the ramp, there will be two forces acting on it. One is a normal reaction, which will make sure that the hoop, the center of the hoop does not fall below the red line, and the second one, which is frictional force, which probably will change the angular momentum of the hoop. Now, what kind of motions are possible here? So, I will categorize these three motions in a separate way. So, the first motion is when hoop is bouncing off the ramp. So, it sort of comes here and then touches. So, at this point the hoop will probably touch the ramp and then goes off. So, while it is in the air not touching the ramp, there is only gravity acting on it. When it touches the ramp, then both normal reaction and the frictional force will work on it. The other motion which is of interest to us is when the hoop stays in contact with the ramp all the time. That is, sort of rolls up and down and possibly even slide. Okay. So, the friction is not large enough. If the friction is not large enough, and also if the initial conditions are not set properly, then the rolling is not possible. Remember, however large the friction is, it crucially depends on the initial conditions. See, you can think of it like this. It does not matter how large the friction is. If I take a spinning hoop and just keep it on the ramp, there will always be a initial sliding, because at initial point itself, the constraint which is obeyed by the third kind of motion, which is the speed of the center, is r times the angular speed. That is not obeyed, which means the sliding will anyway happen. And the third one, third variety is here, where the motion occurs without sliding. So, that is a rolling motion. Okay. Remember, rolling motion means you also have to set the initial conditions properly. The hoop remaining in contact with the surface also requires you to set initial conditions with care, otherwise it will not happen. So, but anyway, these three situations can be dealt completely differently from each other, and this is what will follow in the remaining part of the calculation. Okay. So, what I want to do is this: the two forces, normal reaction and the frictional force, I want to write these in the form of generalized force. So, basically I want to write that as the force with a component along x, component along y and component along theta. Okay. So, let us start calculating. Before that, what kind of trajectories that these three motions will give? So, I am showing this in the configuration space. See, the first kind of motion where the hoop is above the ramp, think of one simple case. In a simple case, I just drop the hoop from some height, I will go and bounce off the ramp and bounce in some other direction, and see what will happen. If I just drop it without any spin, it will go, when it touches the ramp, there is a normal reaction, but there is also friction. Friction will exert torque, and when it bounces off, after the bounce it may actually acquire spin, and when it acquires spin, what happens to the theta coordinate? You can see in this green trajectory, after the bounce, once it's in the air, of course there is only gravity acting on it, angular momentum will remain conserved. So, the theta will vary only linearly from the point of bounce, and truly speaking, what happens at the bounce is fairly complicated. That usually will require some sort of a modeling of normal reaction and the frictional force. You can easily visualize variety of situations. You take a hard ball bouncing off a hard surface, or a soft tennis ball bouncing off a softer surface like clay court or something like that. The interactions are completely different, and the modeling of those interactions is also hard, but that of course is not our focus here. The second kind of motion here, these ones, the hoop is always in contact with the ramp. Remember, all the trajectories here, because of that non-holonomic constraint that y minus x tan alpha is greater than or equal to 0, they must happen above this plane. Okay? No trajectory can go under the plane. And then for the second case, you have trajectories. So, these trajectories will remain on this plane. The equation of this plane is in fact y is equal to x times tan of 30 degrees. So, everything happens above or on the plane. For the second case, the motion, the trajectories are restricted to this plane. But what kind of trajectories are possible? Any trajectory is in fact possible. One representative trajectory which I have shown here in the red color, this clearly says that there is a sliding. So, you can see that the constraint equation for rolling motion, for the third kind of motion, is the, suppose if I measure the distance or just write velocity v or speed v of the center of the hoop, that must be equal to minus r times theta dot. This is the constraint for rolling motion. Now, this constraint immediately tells you that the trajectories must be of the black kind. It is a straight line trajectory, so that the velocity component along theta direction and along v direction, they maintain its ratio, and that is exactly what does not happen here. So, you can see that the velocity vector, if I draw here, velocity vector has two components, one is v, which I have written here, and the other one is theta dot, which is here, and these have a constant relationship, but you can see that as you go here, probably that relationship has changed. And it is also, there is a minus sign which is missing here. In this trajectory, black trajectory, of course, wherever you take the, so the two components at all points there, theta dot and v dot maintain its relationship, the linear relationship or the ratio is constant as minus r. So, these kind of trajectories are what are going to happen in your configuration space. Now, let us look at the forces. So, here I will show that ramp by some part of the ramp here, and you have this all the n segments. Remember, the normal reaction and frictional force will only act at this point, at the point of contact here, at the point of contact here. Okay. So, they are actually acting on only one segment out of all the n segments there. And which segment would that be? Remember, this angle is alpha, and this segment I will call it as kth segment. Okay. So, kth segment is touching the ramp. Okay. Now, what must be this angle? So, this angle here is this angle here is theta, and this angle here is alpha k for the kth particle which is touching, or kth segment which is touching the ramp. And what must be the value of alpha plus theta k? That we can immediately see from geometry, that this must be total angle measured from the horizontal axis or positive x axis, which is theta plus alpha k, that must be equal to 3 pi by 2 and another 30 degrees here. So, alpha plus theta k must be equal to 3 pi by 2 plus pi by 6 for that segment which touches the ramp. Okay. So, what is the force on this one? Its normal reaction is perpendicular to the ramp. Okay. So, we can again write down that as magnitude. Remember, the magnitude is still unknown to us, but the direction we know. Direction is nothing but the cos of, so for this angle it is a minus cos of 30 minus sine of 30 degrees, and the y component will be cos of 30 degrees. Okay. So, we know this direction. Now, let us write down the generalized force for this normal reaction. Okay. or express this normal reaction as a generalized force. Okay. So, the Rk here is x plus r times cos of theta plus alpha k, and y component will be y plus r times sin of theta plus alpha k. And remember the formula for generalized force, what we actually need in that are the derivative of r k. In fact, we will, for that formula we need derivative of r I for any ith particle or ith segment with respect to x, and that is just I cap. Here r k is here. So, the derivative with respect to x will give you only I cap. Derivative of r k with respect to y will just give you j cap, and derivative with respect to theta here will be, of course, x, y and theta are independent coordinates. So, it will be minus r of derivative of cos is sin here, and similarly for y component it will be plus r times cos of theta plus alpha k and j cap. Okay. And this I will write in a compact form like this. Now, let us put this and calculate the. So, the q and x, remember generalized coordinates, generalized force will be given by q x component, q n y component and q n theta component. Okay. So, we calculate the x component here. Q n x is nothing but sum over I, sum over all segments, f I dotted with del r I by del x. But we know that f I is 0 for all I except 1 when I becomes k. Okay. So, this is your again kth particle, kth segment, and this angle being theta plus this angle of alpha k. So, when you take a partial derivative of, so when you take this sum, only one term contributes, which is f k dot product with partial of r k with respect to x. Okay. And that is, we have already calculated this one here. So, I will put that there, which is I cap, and f I, remember we already have written, we know the direction of this. And when you take the dot product of these two, I just get q n x is n by 2. In the same way, if I calculate q n y, now the same f I or f k dot product with j cap, and that gives me 3 by 2, a square root of 3 by 2 n. And I will now calculate theta component. In case of theta component, something nice happens. So, this is your f I, and this we have calculated as partial of r I or partial of r k with respect to theta. I forgot to write r there, but these two vectors, they are perpendicular to each other. So, the q n theta becomes 0. So, finally, the three forces together, q n x, q n y and q n theta, this is nothing but minus n by 2, then square root 3 by 2 n and 0. And similarly, the frictional force is of course the force which is parallel to the surface of the ramp. So, this is your frictional force there. And what is the frictional force in the real with Cartesian coordinates? Oh, that of course would be simply given by half, so sorry, square root 3 by 2 I cap plus half j cap, that is this direction here. And partial of r I with respect to x, y and z, x, y and theta, they are same. So, I can now repeat this calculation for frictional force and calculate the coefficients or components along the directions of generalized coordinates, except that the theta coordinate theta component is given by R f, because remember in that case the, or if you want me to write here, this will be f, and you would have half root 3 by 2 I cap plus half j cap dot product with, remember it was del r k by del theta, and that will be in fact root 3 by 2 I cap plus half j cap into r, and this dot product is actually just 1. And not surprisingly, it turns out to be r times f. What is that? That's torque about the center. So, the frictional force is actually just torque about the center of the disk. Okay. So, now we have calculated this. Now, I am going to go back and look at all those 3 motions as they or the way we are going to describe them. Okay. In the first case, okay. So, before that I will also show you the directions of the forces there. Okay. So, the first case, so remember look back at these equations. So, here I can also write this as minus half root 3 by 2 comma 0 into n. The direction of this force in configuration space is fixed, only the magnitude changes. What about this one? So, for frictional force qfx, qfy and qf theta, this also is in fact root 3 by 2 half r times f. Okay. And all these 3 numbers are constant. So, what will happen is this: whatever the trajectory is, whenever the normal reaction and frictional force will operate or act on the system, the direction of these forces in the configuration space is fixed, and which is given by this vector here and this vector here, except that the magnitude is given by the actual f here and actual n here. Okay. And when I put that in the configuration space, I see this. Okay. So, I have shown them at one point, but remember the direction of the normal force is always perpendicular to the surface and parallel to this vector which I have shown here, and the magnitude direction of frictional force will be in this direction, which is in the plane and has a theta component. Okay. So, this would be your direction where theta component is 0, but normal frictional force will have a theta component. Okay. Look at its relationship with these 3 trajectories. So, in the first case, in the green case, where the hoop actually goes into the air, the frictional force and the normal reaction acts only when the hoop touches this surface in the configuration, or the trajectory touches the surface in this configuration space, and the direction of n cap and theta cap. So, they are of course neither parallel nor perpendicular to the trajectory, and something will happen as a result of that. What about the red trajectory? In case of red trajectory, notice if you take any point here, the normal force is always perpendicular to the trajectory. Okay. The normal force here in fact will enforce, because now the constraint is a holonomic constraint. What happens for the red trajectories? The hoop is in contact with the ramp. So, y must always be equal to x tan of 30 degrees. Okay. So, in this case the constraint now is holonomic and the constraint is enforced by the normal reaction. So, the normal reaction will always be perpendicular to the constraint surface. Remember, this is the constraint surface. So, it will always be perpendicular to the constraint surface. But this one, the frictional force is not perpendicular to the trajectory, for the red trajectory. That is because there is a sliding happening, and in case of sliding where the frictional force is doing some work and there is no constraint really. Okay. Whereas, a third case of the black trajectories where the motion is rolling without slip or without sliding, what happens? Now, you have a constraint, and what is that constraint? Velocity or speed is r theta dot. This constraint, remember, in this case this constraint is integrable and hence it is actually a holonomic constraint. So, and this constraint is enforced by which force? That is the frictional force. So, look at what happens. The trajectory is a straight line trajectory on the constraint plane. So, you have one more constraint which keeps the particles on the black trajectory, and your constraint forces, two constraint forces, one is normal reaction, one is a friction, both of them will be perpendicular to the accessible configuration space, which actually are the straight lines in this. Remember, depending on the kind of initial condition that you set, the trajectories could be different. The trajectories could be something like this or something like this, but in all these trajectories the constraint, this constraint is always obeyed. So, this is the third kind of and this is where the forces act as constraint forces. So, to summarize, here are the three situations. In these three situations, the first case where the motion is above the ramp. Now, let us write down the Lagrangian for this system. What is the Lagrangian? Lagrangian, of course, in this case there is no constraint. Okay, there is no constraint. So, Lagrangian is function of x y theta, x dot y dot theta dot, and this Lagrangian we have already written. Out of this, gravity can be expressed in terms of potential. So, we put it on the left hand side of the equation of the Lagrange's equation and make it part of the Lagrangian. That is why the gravity appears here in the Lagrangian. What about the normal force and the frictional force? Those forces are not constraint forces, they have to be taken into account, they are active forces, but I can't express them in terms of potential or generalized potential. That means, in the equation of motion, these forces will appear on the right hand side here. Okay. So, the three equations of motions would be from the Lagrange's equations. Mx dot will be equal to qnx plus qfx. Remember, we have calculated all these components in the previous section, and also remember that these forces are actually 0 when the hoop is in the air, and these forces are non-zero only if the hoop touches the ground. So, hoop touches the ramp. If you want, we can multiply this by delta of y minus tan 30, or this particular delta function could be included in the magnitude of n and magnitude of f itself. But either way, you have to take this force into account, which appears on the right hand side of the Lagrange's equations. When the motion happens on the ramp, but probably with sliding, now we have one constraint force, that is normal reaction, and now we will incorporate that holonomic constraint into your Lagrangian formulation. What does that mean? I can forget about the normal reaction. So, the Lagrangian now, so the constraint, of course, I will write it as y is equal to x by square root 3, that is x tan 30, but I will use another generalized coordinate which is s by 2, y is equal to s by 2. That is actually the length measured or the distance measured along the ramp. Okay. Now, the Lagrangian is written as function of s theta. Remember, the degrees of freedom have reduced to 2 for this kind of motion. I need only 2 generalized coordinates. So, one of the generalized coordinates is going to be s, and the other one I am going to use other one is the theta. So, the Lagrangian is function of s theta, s dot theta dot, and we can actually calculate the new Lagrangian from this Lagrangian very quickly by using this equation. Y is equal to s by 2 and x is equal to square root 3 by 2 times s. And that Lagrangian, not surprisingly again, is just the kinetic energy plus rotational and translational kinetic energy plus rotational kinetic energy and minus the gravitational potential. 2 Lagrange's equations, let us write those down. The equations of motion, of course, this will come from d by dt of del L by del S dot, and this on the right hand side what goes is only QF. There is no Qn on the right hand side, because that normal reaction was a constraint force whose constraint has already been incorporated in the Lagrange's in the definition of Lagrangian. And then the second equation becomes mr square theta dot theta double dot is equal to Rf, but of course, that we knew it is the angular momentum and that is a torque. So, it is a derivative of angular momentum dl by dt is equal to torque. And now, let me look at the third possibility. In the third possibility, there are 2 constraints. The first constraint is of course same as the previous one, which is y is equal to x by root 3. The second constraint is s dot is equal to minus r theta dot. So, what I am going to do is this. Remember, now in the previous lecture, I have derived this theory of, or I have found a way of incorporating non-holonomic constraint. Now, I can of course think of this as a non-holonomic constraint. I will do that in a moment, but before that, let me treat this as a holonomic constraint, because I know I can integrate this and I will get an equation like this. Okay. So, after integration, when I get this equation, after integration I get this equation. Now, same thing, calculate the Lagrangian again, but now the Lagrangian is function of only one generalized coordinate. You can choose that either to be s or you can choose that to be theta. So, the Lagrangian is function of theta and theta dot. Same trick, you already have equation between s and theta. So, wherever s dot was there in the previous Lagrangian, replace it by the theta dot minus r times theta dot, and wherever s was there, replace it by minus r times theta minus theta naught. That gives you this new Lagrangian. Equation of motion, just one. Write that there, mr square theta double dot is equal to 1/4 of mgr. That is your, and this we could have gotten from, that is why I said this was a very simple example, but you see it actually is showing us different trajectories in configuration space and how the Lagrangian formulation can be applied to a problem. Now, finally, I will also treat the same constraint as a non-holonomic constraint. Okay? And remember the definition of Pfaffian. So, now I will write this constraint in the Pfaffian form. It is ds plus r d theta is equal to 0. Remember, I will write the Pfaffian form again. If I have just one constraint, then I will write the Pfaffian form again, and that would be Bj dQj plus B dt is equal to 0. Remember, if I just have one constraint, one non-holonomic constraint, then I have this. If I have many constraints, then remember in the previous case I had written that as Bij dQj plus Bi dt is equal to 0, but we only have just one constraint. So, now what is your Bs? So, this basically we will write it as Bs ds plus Br d theta plus B dt is equal to 0. And if you compare that with the Pfaffian form here, then you can immediately write down Bs must be equal to 1, B theta must be equal to R, and B must be equal to 0. Okay, fine. Now let us apply this. And how do we write the Lagrange's equations for non-holonomic constraint? Start by writing Lagrangian. Lagrangian now is not function of one variable, but it is function of two variables. So, it will still remain function of s theta, s dot and theta dot, okay. And that same Lagrangian will be there. When we write the Lagrange's equations, remember we would have, so the Lagrange's equation is d by dt of del L by del Qj dot minus del L over del Qj, and on the right hand side you have B, so lambda, which is multiplier multiplied undetermined multiplier and multiplied by Bj. Okay. So, this side of the equation, which we have already calculated, gives us ms double dot plus half mg. On the right hand side I must write lambda times Bs, but Bs is nothing but 1, so it is just lambda, and mr square theta double dot, which is the left hand side of the equation, must be equal to lambda times B theta, and that will be equal to lambda times R. Okay. So, these are the two equations you get, and we must solve them because lambda is unknown. We must need a third equation, but what is the third equation? So, I will first calculate s double dot in terms of lambda, theta double dot in terms of lambda again, and the third equation we need for determining lambda is from this equation. If I divide this by dt and take one more derivative, I get s double dot plus r theta double dot must be equal to 0, and then I put s double dot which I have obtained from here, theta double dot which I have obtained from here, put it back in this equation, that immediately gives you lambda is equal to 1/4 mg, and this we immediately recognize is nothing but the value of the function. This is nothing but the value of frictional force. There we go. So, this is the problem, this is the example where we have done everything. Okay. Each one of these separate kinds of motions, if we know, if we have guarantee that they will happen, that also means that the initial conditions must be set properly, then I can treat all these situations differently, write different Lagrangian and treat forces differently. Remember, in the first case the normal reaction and the frictional force were just active forces. In the second kind of motion, normal reaction becomes a constraint force, frictional force remains a active force, and in the motion where you have rolling without sliding, both normal reaction and friction can be thought of as generating a normal reaction generating a holonomic constraint and frictional force generating the non-holonomic constraint. And of course, we can apply all that technique that we have developed to solve the problem here. Okay. So, this sort of concludes our discussion on Lagrangian formulation. From this point onwards, I will briefly this week introduce the notion of a phase space, and then we will conclude this week. Next week, we will learn about the Hamiltonian formulation. Okay.